Hey everybody, we are talking about polynomial functions of higher degrees. Remember that a degree is the highest exponent in a polynomial period. So let's jump in. So something that's continuous has a graph with no breaks. Another way to describe something that's continuous is like if you can draw the graph of the function and you never have to pick up your pencil. Extrema, we talked about this a little bit in class, are just another word for the minimums and the maximums. The root word for extrema is extreme, so the lowest point is the minimum and the highest point is the maximum. A relative minimum is the least value of a function on a specific interval. The relative maximum is the greatest value of a function on an interval. A repeated zero is used like this. Let's say if there's some factor, x minus some number, we look at that as a factor, we don't know what the degree is. It could be to the first, to the second, to the third, we don't know. As long as n is greater than 1, then x equals a is a repeated zero. And keep in mind that the x-intercept is also known as what's called a zero, a solution, and as a root. So don't forget that if you don't have that written down yet. A multiplicity. So a multiplicity is the number of times a zero is repeated. And then the last one is intermediate value theorem. And this one is going to feel foreign to us when we start because this is kind of more of a formal math theorem, but this is a really important theorem. So it says let A and B be real numbers. Okay, so we're thinking, okay, any two real numbers where, and so we say such that just means, okay, so another thing that we know about it is that A, it has to be less than B. So think of two numbers where one is less than the other. If such that, so then another thing, if the function of A is not equal to the function of B. So if I plug in these values of A and B, that their y outputs are not the same. And the interval where x equals A to x equals B, so remember from left to right, then we say f takes every value between the value of that starting point f of A and the ending point f of B. So one way that we can kind of see this when we're describing that, so let's just say we're looking at this and we've got some function, I don't know, we'll say it looks like this. We'll call this value right here is A and this value right here is B, okay? So on the graph, this point right here is f of A and this point right here is f of B. So here's what we know. We know that A is less than B. We also know that f of A, this value right here, is not equal to f of B. So from the values of f of A, which we'll say that's pretty much 0, to f of B, well, I don't know what value that is, some positive value, that this graph in here, for every value in between on the x value, we have some value of f of those values of x between A and B, that takes every value in between from here to here. That everything is covered, meaning there's no holes, there's no disconnects. All right, let's do the next one. So name two basic features of the graph of polynomial functions. Number one, they have to be continuous, meaning you don't pick up your pencil when you draw them, and they are rounded with smooth turns. Okay, so we don't see any sharp edges or anything. Everything's rounded with smooth terms. So let's talk about this one. Will the graph of g of x, where x is to the 7th, look more like f of x where x is squared, or f of x where it's cubed? And because we're looking here primarily at the exponents, see that this one is an odd number, so is this one. So we know f of x, where x equals to the 7th, is going to look more like f of x, where x is to the 3rd power, because they're both odd degrees. And if you want to look at that, here is x squared, we know looks like this. This is x to the 3rd, looks like this. And x to the 7th looks something like this. Okay. So let's talk about what the leading coefficient test is. The book says it specifically, but I wanted to give you a visual representation of this, so we're not going to worry about that. So here's what the leading coefficient says. We're looking for, on the leading coefficient, we're looking to see, so if let's say, for example, you've got f of x equals ax to the nth power dot, 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 okay? If a, we're looking at that leading coefficient, is positive or negative, there's two different situations. And then we're looking for this exponent. We're looking to see, okay, is that exponent even or odd? There's two different situations there as well. So this is our degree, or the exponent is even or odd, and the leading coefficient is either positive or negative. Here's what we know. If, and then these little black things in the middle is, I don't know what's going on in the middle of our graphs, but I'm just talking about the leading coefficient test tells us the end behavior of our function. So here's what we know about every positive function ever. It always ends to the right going upwards. So if it's even and positive, it goes to the right. Also, if it's odd and positive, it goes to the right and up. If it's negative, and no matter what, it always ends down, just like our frowns. If they're even, they end up. If they're negative, they end down. Now, here's where the other part works, whether it's even or odd. If they're even, both sides of your graph match up. So the beginning and the end will be going upwards. Whereas if they're odd, they're going to be mismatched. So the beginning of our graph to the left will be going down, where the right side is going up and to the right. Again, if they're even, they match up. So if it's negative, both left and right sides are going downwards, whereas if they're odd, they're going opposites of each other. So here's what that means. If it's an even positive, both endings to the left side and the right side are going to end up. If they're odd, we're starting from the bottom up, going this way, and then we're going to end to the right up. If they're even and negative, they're going to go down on both sides. If they're odd and negative, they're going to begin on the left side upwards, and they're going to end on the right side going downwards. So let's talk about describing that left and right behavior of this graph. So first and foremost, we need to make sure that this is in descending order, because we need to see what the leading coefficient is. So we need to put this in descending order. So it means I'm going to rewrite this as negative 4x to the 6th minus 3x squared plus 1. This tells me that I'm looking for my leading coefficient and my degree. So because my leading coefficient is a negative, we're going to be looking for a negative, and our highest exponent is 6. That's an even number. So if I look back up here, negative and even, I'm going to go, here it is, negative, even. That's this graph right here. So I know my end behavior is going to match, and they're both going to go downwards. So what I'm going to say about that one is I'm going to say, well, I know I'm going to be going down to the left and down to the right. And that's all you have to say. Now let's talk about zeros of polynomial functions. Remember how we talked about zeros are the same word as x-intercepts? Let f be the polynomial function of some degree. That's just the highest exponent. That the function of f has at most, let's say n zeros, right? Because that degree is n. So whatever the degree is, it tells me how many the maximum of the real zeros are. And then the graph at most, it has n minus 1 extrema. And so here's an example of why. So let's say, for example, you have x to the third, okay? X to the third looks like this. We can see here that our zeros, there's only one of them. So we knew that there couldn't be more than 3, and that n minus 1 is our relative extrema. So our relative extrema, we really only had 1 here, but we know that there's not going to be more than 3. We can also see like this one is an x to the third type of graph, where we see that there's only 2 extrema, okay, and that there's 1, 2, 3 of those x-intercepts or zeros. Okay, so here's what we know. We know if we've got a polynomial function and a is a real number, here's what we know. That we know x equals a is a 0 of f of x. We know x equals a is also a solution to when f of x is set equal to 0. We know x equals a where a comma 0 is the x-intercept of the function. And then the last one is that x minus a is a factor of f of x. And we've seen that, right, a few times over, where x minus a, when I set it equal to 0, I end up getting these x equals a. All right, we're almost done. If a polynomial function has repeated zeros, like x equals 3 is a 0 with a multiplicity of 4, remember how I talked about if it has an even number of multiplicity, it kind of kisses or touches the x-axis at the value of x equals 3. So this is what it would look like. If here's x equals 1, 2, 3, if it has a multiplicity of 4, it's going to look like this and bounce off of it or just barely touch it, okay? Whereas if f has a repeated 0 at x equals 4 with a multiplicity of 3, the graph will cross the value at that root of x equals 4. So that would be like, this is the root, but a multiplicity of 3 will go right through it. Okay? So let's sketch the graph here. So a couple things that we know. We know it's positive, even, and we know it hits the graph at y equals 3. So I know it has this 4 degree. We also know that a 4 can possibly move up to 4 directions. So I know it's going to end positive. So it could look something, it's going to end positive on both sides. So it's going to look it could look kind of like a W. So do you see here? So we ended to the right up, the left is going up, and we changed direction. This is a 4. It can go 1, 2, 3, 4. It can have 1, 2, 3, 4 zeros. And we know we have this y-intercept value of y equals 3. All right, almost finished. let's talk about the intermediate value theorem a little bit. So interpret the meaning of the intermediate value theorem. So here's what this says. If we have some value of a for x, then if I plug in a equals x into the function, I get f of a is our y value. Same thing for, we have some value for b for x, and then f of b is going to be that corresponding y value. And then, of course, we have to say, well, I don't want f of a to equal f of b. Okay? Then there is a value, we'll call it d, that we're looking for. But it's between f of a and f of b, where some other value c is x. So if I plug c into x, I'm going to get that value of d for y. So how can we use this tangibly? So how can we use the IVT, intermediate value theorem, to help us locating real zeros? Well, here's what we can know. If you have values where f of a is a negative value and where f of b is a positive value, then we know, because between a negative and a positive value, there's got to be a zero. So then we know at least 1 0 between where x equals a and b has to exist. So that's one way that we can look for zeros. All right, I'll see you back in class.